Good evening. It's great to be here, and it's great to have IMS back in Boston again. Many of you were probably as impressed as I was to see the image behind me, which is an image of the black hole that's at the center of the Messier 87 galaxy. This black hole is 55 million light years away. And this was a huge accomplishment for astronomy, because up until this image was created, black holes they were predicted by theory. And the existence of black holes was identified by inferring the way black holes affected the relationship of other celestial bodies. But this is the first time that a real visual evidence of a black hole was seen. And so it's a real accomplishment for astronomy. But for me, what's really impressive is the technology that went into making this image. And we all know that a black hole actually can't be visualized because even the light can't escape the black hole. But what this image actually is this is an image of radiation that's generated by particles around the event horizon. And these particles that are under enormous gravitational forces accelerated toward that event horizon emit X-ray radiation. And so this is a microwave sensing problem. And this image was created with a telescope called the Event Horizon Telescope that senses this microwave radiation. Microwave radiation is an X-band, and actually these telescopes have a very high performance receiver, receive about 1 gigahertz of bandwidth in X-band. If you think about the amount of resolution that's required, it's really impressive. So it's very impressive to have a high performance receiver, but it takes more than that to create this image. The resolution that's required for this image is 4,000 times the resolution of the Hubble Space Telescope. It's equivalent to the resolution that would be required to see an orange on the surface of the moon. And so the way this resolution is accomplished is with a synthetic aperture. And it turns out this synthetic aperture is about as big a synthetic aperture as you can get and still have that on the surface of the Earth without going to space. And that's what's called here in the Event Horizon Telescope. So each of these telescopes was part of this measurement, and each of these telescopes has a very high performance millimeter wave receiver. But what's really impressive about this synthetic aperture is what does it take to synchronize all that information and to correct all the impairments in the aperture. The real challenge is that. The synchronization can be done with GPS and atomic clocks, and that synchronization is equivalent to the time synchronization of less than 1 second in 1 million years. But beyond that, there are enormous impairments that have to be corrected in this system. If you think about it, there's impairments of weather conditions. The weather conditions might be different at each one of these telescopes. But there's also other impairments. They have to correct for the rotation of the Earth. But it's not just the simple rotation of the Earth. You have to correct for motion of the tectonic plates, motion of the oceans, the rotation of the core of the Earth. If you think about the amount of data that it takes, it's very impressive. And so this is a great example of a microwave sensing problem. But the challenge and the innovation is not just in the high-performance microwave receiver, but in the digital correction of all those impairments. And to give you a feel for that amount of digital data, each one of the telescopes in this array downloaded 5 petabytes of data. That's 5 million gigabytes. And that data had to be fused together for correcting all these impairments. As a matter of fact, it was so much data that it's not practical to network. They actually physically flew the hard drives to a central computer. So this, I think, is a great analogy for what's going on in our industry in the RFIC world. Our innovations today are coming not just from high-performance RF and microwave circuit design, but from that recombinant innovation of advanced digital algorithms and technologies as well. I'll talk a little bit about that today. So at Analog Devices, I'm responsible for the automotive, communication, and aerospace and defense business. And these are the business units at Analog Devices that are primarily responsible for the RFIC design that we do. But stepping back at Analog Devices, we say that our company exists at the interface between the physical and the digital world. Our strategy is to create the most high-performance technologies to sense, measure, interpret, connect, and power. And through those technologies, we are providing that connection to the physical and the digital world. If you think about RFICs, what we do in the RFIC industry is also really about connecting the physical to the digital world. RFICs are about connecting the electromagnetic spectrum to the digital world. There are two main application drivers for RFICs today. Those application drivers are communications and sensing. Communications is the application driver that most people are familiar with. And I would say if you talk to the average person in the street and you ask them about RF or wireless technology, they will most often think about communications. And the communications that they're most familiar with are typically what we would call the consumer applications: cellular handset communications, Wi-Fi, and Bluetooth. And we all know how ubiquitous those communications have been. I bet you every person in this room has at least one device that has all three of those technologies integrated in it, maybe more. But there's a lot of other applications, communications applications, that are driving RFICs as well. And those are more higher performance applications, what we often refer to as the B2B applications. So that might be the infrastructure side of cellular communications, microwave radio, and satellite communications, to name a few. Another great driver of RFIC technology is sensing. I would say that sensing is not as commonly thought of as an RFIC technology or as a wireless technology, but the applications of sensing are exploding around us. There are some applications of sensing that are very familiar to us, maybe be air traffic control radar or weather radar, but there's also a lot of new and emerging applications of millimeter wave sensing. Autonomous driving, automotive radar for autonomous driving, millimeter wave body scanners for security at the airport, and a lot of new applications of sensing around medical and biological sensing applications. If you think about this, these applications tend to drive RFIC requirements, but also RFIC capabilities are enabling these applications. We see this as a cycle of innovation. It's not just that RFICs enable the applications, but the applications also drive RFICs to have new capabilities. So if you think about it, advances in RFICs are enabling new applications every day. And once those applications are enabled, and as we talked about, RFICs are connecting that physical and digital world, those applications tend to drive more and more data. And through that more and more data, it puts pressure on the ecosystem to create even higher performance solutions to advance those applications further. And there's kind of two rotations of this cycle that I would like to talk about today. The first is really the emergence of CMOS for RFIC applications. We all know that CMOS has made a huge impact on our industry. And if you think about CMOS and RFICs, it was a topic of academic papers maybe back in the 80s, but it really came to its own, I would say, in the 1990s, and it came to commercialization. And CMOS was largely responsible for making many of these consumer-based technologies really ubiquitous like they are today. Wi-Fi, Bluetooth, and cellular handset communications. The advantage of CMOS is that it brought scale and cost structure to RFICs to really allow these technologies to become ubiquitous. And clearly we know that Wi-Fi, Bluetooth, and cellular communications are ubiquitous. And further, we know that the demands on these technologies is increasing every day. On average, the average user bandwidth of wireless technologies doubles about every 2 years. And so that cycle then puts more pressure on the RFIC community to iterate those further. But there's another whole ecosystem of solutions that have been enabled by CMOS-based RFICs, and that's beyond just these consumer applications that we refer to as the B2B applications. And these are applications that typically had higher levels of performance requirements than you would have in the consumer solutions. So it might be the infrastructure side of cellular communications, for example. To get the CMOS technology to be able to deliver on those applications requires innovation beyond just what you can do in that core CMOS circuit design. It requires what we will talk about as a recombinant innovation. It's a combination of high-performance CMOS circuit design, RF and microwave circuit design with digital techniques in what we would refer to in this presentation as digitally assisted CMOS. These digitally assisted CMOS capabilities are really driving the solutions that we think about emerging today. That of infrastructure for 5G and radar required to get really, truly autonomous driving. So what I'm going to do today is talk about two examples of this digitally assisted CMOS. One of these in the communication space, and that'll be infrastructure for 5G, and one of these in the sensing space, which will be advanced radar capabilities for autonomous driving. So turning first to the communication space, to set the stage for this, I'll talk a little bit about what was the state of the art for cellular infrastructure circa 2013. So I have a diagram here. On the left-hand side is what a base station circuit, what an LTE base station circa 2013 would look like from a circuit perspective. And on the right-hand side is kind of the block diagram of that circuit. So this would be an LTE base station, a 2-channel LTE base station, 2 transmit channels, 2 receive channels, and 2 observation paths for linearization. And you can see that this was kind of a very traditional architecture, a traditional heterodyne architecture. There's obviously a lot of RFICs and a relatively high level of integration. If you looked 5 years before that, you would see a much larger number of discrete components. But the point I want to make about this is that this is the level of integration that was available in RFICs to meet the performance requirements of LTE. And there's a number of different technologies here. The blue typically were BiCMOS technologies. The orange were CMOS technologies. But the other thing you note, being a heterodyne architecture, has had a lot of high-Q filters that you had to go on and off chip to get those high-Q filters to get the filtering requirements. And if you really wanted to get more levels of integration, like as typically we would get in say, the handset space, you had to go to a completely new architecture. That architecture is similar architecture that you would have in the handset space of a direct conversion architecture. But to get to direct conversion architecture with the performance levels that you need in base station required significant levels of innovation. A number of things needed to happen. One, you had to go to circuit design that was very CMOS friendly. So the reason that BiCMOS was used for many of those base station applications in the previous slide, because bipolar devices give you a lot of gain. So they're very good at giving you high gain, low distortion circuits. So you had to go to a CMOS-friendly architecture. But beyond that, you need a lot of digital enhancement of the circuitry. Another key feature of this integrated solution is to use sigma-delta ADCs. Sigma-delta ADCs have an inherent anti-aliasing capability that allows you to use relatively simple filtering and eliminate all those high-Q filters in the previous block diagram. But that is also not enough. You have to have significant digital correction algorithms to be able to get the performance levels that you need for base station. So there's significant digital that's integrated into this for distortion correction, IQ correction, and basically for correcting the impairments in the system. You can think of this analogous to the M87 image I showed you before. The digital assistance is correcting for the impairments in the RF system in order to be able to meet those requirements. So this is a solution we brought out in about 2016. I showed the chip diagram over on the left-hand side. This is a 2-channel single carrier LTE base station developed in 65 nanometers CMOS. I note here on the next slide that this capability of single carrier LTE, and you can see the digital block shown there. So that's the amount of digital content. And I show that for reference because as you see this progression and as you see the performance enhancement proceed, you'll see the amount of digital that it takes to meet those level of performance requirements goes up. So this was really an accomplishment because it was the first time to have a fully integrated CMOS solution for cellular infrastructure. But as we all know, single carrier LTE is not the whole market, and the market is evolving, and the market has evolved from single carrier to multi-carrier. And in addition, it's not just multi-carrier LTE, but if you really want to meet the majority of the base station market, you have to have multi-carrier LTE with GSM capability. And the presence of GSM and LTE at the same time puts significant stress on the receiver performance. So to go from the single carrier LTE to GSM and LTE multi-carrier, it's about a 30 dB improvement in signal-to-noise ratio and about a 50 dB improvement in spurious-free dynamic range. So the main things that were done there, significant improvements in circuit design to get the SNR. On the right-hand side, you'll see that solution, which is also designed in 65 nanometer CMOS. It's also a 2-channel, so the significant increase in die size is really related to getting the higher signal-to-noise ratio. But the key to getting the high spurious-free dynamic range is significantly improved linearization techniques and compensation techniques. And you can see the amount of digital increase there is about 8 times the amount of digital content to get this to happen. But now we have a solution that is fully integrated CMOS for GSM and multi-carrier LTE. The next innovation that has come from this, though, is that the market has moved just from multi-carrier LTE to massive MIMO. And the reality is that if people are familiar with massive MIMO is where you go from, instead of having a base station that has 2 channels or 4 channels, a massive MIMO base station might have 64 channels. And the reality is that massive MIMO would really not be possible without this level of integration in the RFICs. So our massive MIMO solution is now done in 28 nanometer CMOS. This is a 4-channel, 4-transmit, 4-receive, 0 IF solution supporting multi-carrier LTE in a massive MIMO solution. And the next innovation beyond massive MIMO is that of multiband. So this is still emerging, but the idea is that they want to go, instead of just having multi-carrier LTE where you have bandwidths of a few hundred megahertz, solutions that are bandwidths that are gigahertz wide. Today, our solutions for multiband are based on RF converters, another kind of direct conversion architecture. So this is a 28 nanometer solution for multiband, 4 transmit, 4 receive, 4 observation path. And the point I make here is even if it's just an RF converter-based architecture, there's an enormous amount of digital, even more digital than you have in the 4-channel massive MIMO solution. Again, that's for correcting impairments in the circuit to meet the performance requirements you have for base stations. A big advantage in base station market, though, is that once you have all this digital, now you can do other things as well. And in the massive MIMO solution that we have shown you previously, once you have that digital, you can add other capabilities to the system-level solution. And I already talked about how the digital is correcting for impairments inside the circuit. We can also correct for impairments outside of our transceiver. People that know about communication systems know that the power amplifier is always the highest, the lowest efficiency part of the system, and also generates most of the impairments. And typically, that's the reason for the observation receiver. So typically, our transceiver would have an observation path. We'd feed that observation path back to the big digital, which is shown here as an FPGA. They would linearize that through predistortion. But one of the things about linearization is you have to observe a significantly wider bandwidth than you are linearizing. So you have to pass that high bandwidth back. And now that we have that digital capability, we can actually add in the linearization. And it comes at a relatively low cost because we're already in a very advanced digital node. And so we've added in our massive MIMO solutions this DPD algorithm. We can do the DPD inside of our transceiver. It offloads the resources from the central FPGA. And the net power savings is really big in a massive MIMO system. So in a 64-channel massive MIMO system, implementing this inside of our transceiver as opposed to carrying the data all the way back to the FPGA saves about 110 watts per system. It also allows you to reduce the size of that central processing by about a third. Alternately, you can use that processing inside the central processing for something else. So we've shown you the capabilities that we have in digitally assisted CMOS for sub-6 gigahertz 5G. The future is about millimeter wave 5G. I show you here a system on millimeter wave 5G. We're actually announcing our complete bits to antenna system for millimeter wave 5G at this show, and we're part of this summit that's coming up. But you can see the interesting thing about millimeter wave 5G is that this is an area that still has a lot of complexity to be solved. It's an architecture that still has a lot of different technologies. It's an architecture that still uses discrete filters. So I think the future over the next 5 years, the next 5 to 10 years, is going to be bringing these high levels of integration through digital assistance to this millimeter wave space. The next example I'd like to give is that of about automotive sensing for automotive radar. And to kind of motivate this, I would like to talk a little bit about the requirements for radar. Many people are familiar with a communication system, maybe some fewer people familiar with radar systems, and what requirements you really need to have. So for those people that know about designing radar, you kind of have a fundamental trade-off between phase noise, operating bandwidth, and the ramp speed of your radar. So if you have an operating radar, you send out a pulse, you come back and detect an object, and you'll see an object, and this might detect as an object that's coming to you around 70 miles an hour at a certain distance away. If you were able to increase the bandwidth of your radar system to give you, which gives you effectively a higher resolution, and you sent a pulse out with a higher bandwidth, you might note that it turns out that there wasn't just one target detected, but there was actually 2 targets in there, and those 2 targets are moving at different speeds, but the second target was obscured by the first target, and so you only saw 1 target. So the bandwidth of a radar is really about how much resolution you can get. The phase noise of the radar kind of gives you your detection limit. So if you could take that same radar, which has a higher bandwidth, and lower the phase noise, you might notice, you know what, there's not 2 objects out there, but there's a third object out there, which is a motorbike. and that motorbike is coming at you at 150 miles an hour. And if you had too high a phase noise, you wouldn't be able to see that. The other important thing in a radar system is that you need to be able to sweep fast enough that you can unambiguously detect the velocity of each of these. If your sweep is too slow, you would mistake that 150 mile an hour motorcycle to be going at a very slow speed because that velocity would alias down. So you want to have low phase noise, wide bandwidth, and very fast ramp speed. And the challenge is that in a traditional analog-driven FMCW system, there's kind of a fundamental trade-off between those. And I'll show you that on this next slide. This shows the technology that was used in automotive radar circa about 2014. This is a fast ramp PLL that was developed by Analog Devices and released around this time frame. It's used in a lot of production 77 gigahertz systems today. And so the challenge you have with a traditional analog swept PLL is that gray curve there is your ideal sweep. That's the sweep you would really like to have. Now, if you want to get a low phase noise, you want to set your loop bandwidth very low. That gives you a good phase noise. But you can see that the 200 kilohertz loop bandwidth can't really ever approximate that sweep. So you really can't use the 200 kilohertz loop bandwidth to get the sweep speed that you would need to get the unambiguous velocity. If you use a 500 kilohertz loop bandwidth, you'll have a higher phase noise. But now you can at least approximate the sweep. And actually, for about half of that sweep from 5 to 10 milliseconds, you could probably use that. But you realize that the sensitivity of this radar would be significantly reduced because about half the time you would be waiting for the sweep to settle. So you would really lose about 3 dB of your sensitivity. So that would drive you to go all the way to, say, 1 megahertz. And at 1 megahertz, maybe you get 75% of that sweep that you could use. You still have maybe a 20 to 30% dead time, but now your phase noise is significantly higher. And this is kind of a fundamental trade-off, and one of the fundamental trade-offs that radar engineers know very well. And the solution to this, though, was to come up with a completely new kind of PLL. And that was a digitally driven PLL. And so we have developed a solution which is based on a rotating traveling wave oscillator. This is effectively a digital PLL. It's basically effectively a large ring oscillator. So we have a 32-tap ring oscillator where going twice around that loop is a single revolution for that PLL. And the key to this is that it requires a very high-speed digital technology to allow you to have a fast enough delay in each of these gates that you can make this oscillator work. And basically, there's 32 taps around this PLL, and you can adjust the phase as you go around, and allows you to digitally create the ramp. This allows you to completely decouple the loop bandwidth from the ramp generation. And actually, you can very precisely generate this ramp. It turns out there's a lot of other advantages to this as well. You can change your ramp from chirp to chirp, and a lot of other advantages as well. But the key here is that it requires you to go to a very high-speed digital process because this is fundamentally a digital PLL. But once we have developed this PLL actually has best-in-class ramp speed, phase noise, and sweep bandwidth. But once you have that, then you can embed that PLL into a very highly integrated circuit. And we have developed a 77 gigahertz CMOS solution for automotive radar. It's best-in-class performance in terms of range and sensitivity. And I show here this latest product that we're sampling to market now, 3 transmit channel, 4 receive channel, fully integrated 77 gigahertz automotive radar using 28 nanometer CMOS. The key advantage of this as well is once you have this level of integration, you can unlock new capabilities in automotive radar that were not possible before, but are really required for what you need in autonomous driving. This is enabling the concept of what we would refer to as an imaging radar. So those people who work in radar know that often, unless you have lots of antennas, the angular resolution of your radar is typically very poor. So you can tell that there's an object out there, you can detect that there's an object, but it's hard to discern the details about that object. So you can use it for detection, but it's hard to use it for classification. But once you have this CMOS radar capability, we can integrate these together, and we can actually synchronize these to have a combined 4-chip radar, which is 16 channels. And this is enabling sub-1 degree resolution. This is the concept of imaging radar. Now you can use the radar for not just detection of objects, but you can actually use it for classification. And I show over here on the right-hand side the difference between if you just use one of these chips, which has 4 channels, versus all 4 of these chips with 16 channels, you can see that you can distinguish objects that have a much higher angular resolution gives you a much more precise position. And I would say that we're just starting as to the capabilities that we have in radar to fuse this radar together. The future of where this is going to go is to fuse more and more of these radar signals together to give you more and more information about the surroundings around. So I think in closing, I showed two examples of this recombinant innovation. The combination of RF and microwave circuit design with advanced digital techniques to really unlock new potential. In their book, The Second Machine Age, Bjornfelsen and McAfee talk about the value of recombinant innovation, and they study the technology curve of many, many innovations. And basically, any technology, early in the days of that technology, it tends to advance very quickly, and there are kind of exponential increases in capability. But then over time, those increases tend to plateau. And the only thing that ever turns that plateau around is typically recombinant innovation. It's adding together new capabilities of innovation. And this is true in the steam engine, or in the internal combustion engine, or even in the case of personal computing. Where personal computing had really plateaued until came the concept of taking personal computing with wireless communications and a touch screen to make the personal communication devices that we carry today. So our view on the innovation of the future of the RFIC industry is that this is going to continue to be a recombinant innovation of CMOS circuit design, digital technology, and system and algorithm level capabilities. Thank you very much.